All right, everyone. Welcome to our exam review day for Calculus 3, Exam 1. So today is more of like an open-ended kind of day, whereas last time I went over a specific exam. By the way, I posted both the videos for going over that exam, including part 2, which I finished yesterday, I think. And I also posted the video from lecture 11, which was what we were supposed to go over last Friday. But that's not in the exam, so that's not as important. But there is a lecture video up for that now. So you should be able to see all of those videos. Anyways, yeah, let's go ahead and get started. So the way this is going to work is I'm going to do maybe 2 or 3 questions from the chat. And then I'm going to do 1 question from in person because there's a significant amount of people online, only a few people in person. And even that's still technically unfair because there's only like 15 of you guys. But I don't want people in person to feel entirely left out. So I'm going to do 3 questions on the chat and then 1 in person. And I'm going to do it based on questions I find that will be very helpful / questions that a lot of people ask. So for a moment here, maybe like for 10 seconds, go ahead and spam the chat with what you want to be answered here. And don't do it more than once. Don't cheat. Don't do it more than once. Wow, there's like no consistency.
I have a question about showing our screen for the exam because we got a message that we have to use a mirror to show our monitor. Can we do that with a phone camera? Because I don't have a mirror.
You could go to a drugstore and get like a little small hand mirror for like a few bucks or something.
Or you could try and use a CD.
But the exam's today.
Yeah, it's at 8 p.m.
I think the email said you could use your phone to do it.
Oh, okay. All right. Yeah. So yeah, whatever Dr. Huang says is going to go for the exam. All right. Let's see here. Let's actually pick a question here. Let's see here. Let's do the distance between 2 planes right here. By the way, all of the exam details, like all of the logistical details, like what time is it, whether you need to, have a mirror or not. Dr. Huang has already answered all of those questions. So all you need to do is check your email and you'll find the answer to those. So I'm not going to spend time doing those. All right, I will do a question talking about the distance between a point and a plane, or also the distance between 2 different planes that are parallel to each other, which is effectively the same kind of question. So let's see here. Do we have a good question like that from these exams? Let's see here. Here we go. I'm going to do number 12 from fall of 2019 right here. 12, fall of 19. Right there. Okay. Find the distance between 2 parallel, let me move this over. Parallel planes. Let's see, what are the planes here? We have x minus 2y plus 2z is 4. And then we have 4x minus 8y plus 8z is 1. Now, technically, they actually gave you more information than you needed to solve this problem. They could have omitted the word parallel, and they still could have legitimately asked you this question. How could we tell at a glance whether or not these are going to be parallel planes or not? How do we know just kind of by looking at them? Yeah. Right, so the audience says we look at the normal vectors. So the normal vector for this one is 1, -2, 2. And the normal vector for this one is 4, -8, 8, right here. And so the one is a multiple of the other right here. So that means that these vectors are parallel to one another. And if they're both parallel, that means they're pointing in the same direction, meaning the normal vectors are pointing in the same direction, meaning the planes are parallel. So here's maybe one normal vector. Here's the other, which is maybe longer. Here's the one plane. Here's the other plane. And if these normal vectors weren't parallel, the planes would be rotated differently. So these planes are definitely going to be parallel. I'm not sure if they're angled like this or not, but they will be parallel. All right, anyways, let's go ahead and figure out what the distance between these planes are. So the way we're going to do this is we're going to pick a point on one of the planes and then use the distance formula from a point to a plane. So let's see here. I'm going to pick a point on this plane. I'll have x be 0, and I'll have y be 0 for simplicity. And if x and y are 0 in here, then my z value, in order to be on the plane, is forced to be 2. And I recommend picking a really easy point like that, because that will definitely make using the distance formula a lot easier right here. Okay, so we have that. So now what's the distance formula from a point to a plane? Well, that's going to be the absolute value of ax plus by plus cz plus d divided by the square root of a squared plus b squared plus c squared, like that. Now, what are these a, b, and c values, and what are these x, y's, and z's? Well, the x, y, and z refers to the point. So x is 0, y is 0, and z is going to be 2 for this one right here. All right, so then what's a, b, c, and d? Well, a, b, and c are going to be the values of the normal vector for the other plane, and then d is the constant. Now, this d right here assumes that the constant will be on the same side as your a, b, and c. So we technically need to rewrite this a little bit before we can do the formula here. There we go. So our d is actually going to be -1. You need to get -1 over here. How did I get 0, 0, 2 for this? Well, the way I got 0, 0, 2 is I plugged in 0 for x and y right here to make my calculation later easier. And then if I have 0 for x and y, then I put in z equals 2 here to satisfy the rest. So that's where that point came from. All righty, so now let's go ahead and just plug in everything into this formula. Well, we have a times x, which is 0. We have b times y, which is 0. We have c times z, so we have 8 times 2 is 16. And then we subtract 1. All right, what about down here? Let's see. We have a squared, so that's going to be 16. We have b squared, which is 64. And then we have c squared, which is also going to be 64. All right, so then what do we end up with here? Well, we have 15 up here and 144 down here. If we add those together, square root of 144 is 12, and 15 over 12 will be 5/4. So this is going to be our distance right here. Is there a question?
Yeah.
Okay, what's your question?
If two planes aren't parallel, is it just safe to assume that they'll intersect eventually at like some line function?
Yeah, that's right. Yeah, so if two planes are not parallel, then yeah, eventually they're going to kind of crash into each other. Kind of how like if you have two non-parallel lines in 2D space, you're eventually going to have those run into one another as well.
All right, thank you.
Yeah, so in order to even ask a question like this, you need to have these be parallel. Otherwise, this question won't make any sense. It'll just be 0 because they'll crash into each other.
Where did the 16 and -1 come from? I know where they are in the equation. I just don't see the 16.
So this is c times z, where remember c is 8, z is 2.
Oh, and z equals 2. Okay, I see. Thank
and then
you.
d is -1, right? All right. That actually, so why don't we see in the chat again what people want to ask here. But I think I have a question that I want to address that a lot of people want to know. So we'll see if people agree. So spam the chat for a second. This will be the second chat question. Okay, yeah, I am seeing it a bit. So a lot of people want to know about the intersection between two planes and how to find the equation of a line like that. Or maybe you have two lines and you want to find out whether those lines intersect or they're just going to miss each other or they're going to be parallel. So why don't we look for some questions that involve that? All right, let's see here. Oh, here we go. So let's go from the same exam here. Let's go do number 3 from fall of 19. All right. So let's see. So find parametric equations of the line of intersection of the planes x plus y plus z is 1 and x minus 2y plus 3z is 1. All right. So in general, there are 2 ways of doing this. One way is we could solve for one of the variables. Like, for example, we could have x is 1 plus 2y minus 3z, and then substitute that into here, and then solve for one of the other variables. That's one way of finding out what the line of intersection is. The other way of finding out the line of intersection is by taking the cross product of the 2 normal vectors for these planes. Now, why would that work? Why would that one work? Well, if we have these 2 planes and they intersect somewhere like this, so here's the line where they intersect, one normal vector is pointing in this direction, the other normal vector is pointing in this direction. And if we look at a direction that's perpendicular to both of these, that's going to move right along the line. You can almost imagine the line as like a vertical axis for these 2 horizontal axes right here. So if we find the cross product of the 2 normal vectors, then we will get a direction vector for the line that we want. All right, so let's do it that way. I think that way is more likely to get something that appears on the answer choices here. So let's do it that way. We have 1, 1, 1 for this normal vector. And then we have 1, -2, 3 for the other normal vector right here. All right. So then we have I, j, and k, 1, 1, 1, 1, -2, 3. All right, let's see here. So our I component, we have 1 times 3 is 3 minus -2 is 5. All right, with j, we have 1 times 3 minus 1 times 1 is 2. And then j adds an extra negative sign. So we end up with -2 right here. And then finally, with k, we have 1 times -2 is -2. And then minus 1 will be -3. So this is the cross product of our 2 vectors. And this will also end up being our direction vector that we are going to use right here. All right, so far, that means our equations for our line are going to be x is 5t and then plus something. Y is going to be -2t plus something else. And then z is going to be -3t plus something else right here. All right, now how do we know what we're going to put into these spaces right here? Well, we need to find something that's going to be on both of these planes right here. So what you could do, for example, is you can make them have, say, the same x component, for example. So let's say both of these are going to have x's. Well, actually, wait a minute. In order to agree with the multiple choice answers here, oh no, for this one, they actually have the whole parametric equation. We need the whole thing for this. Yeah, so normally what you could do is you could find points that just satisfy both of these right here. But since it's since we need to make sure that it matches up with the answer choices here, and there are a lot of different points on this line, we should probably check the answer choices. So here we go. Let's take a look at this. So let's see here. So there are, let's see. Looks like these 3 are going to match up here with at least our slopes. So these are going to match our slopes. So then why don't we go ahead and try to plug in some of these points here? So let's see. Why don't we plug in C here? So that's plugging in the point 1, 0, 0. All right, will that point satisfy both the planes? Well, let's see. If I put 1 in here and 0, 0 there, then we get 1. And we have 1 on this side too. All right, that's good. And then we have, let's see, 1, 0, 0 here. So I have 1, these will be 0, and then we have 1. Okay, so this point satisfies both of them. So there we go. If that one didn't work, we would simply plug in -4, 2, 3, or we would try 0, -1, 0, and see which one it would end up being here. Yeah, unfortunately, this isn't like the technical mathematical way of doing it. We just need to make sure we get a point that agrees with one of these answers, since it is multiple choice right here. All right, so let's see here. So we went over that question. Let's see, I also want to talk about having two lines and whether or not they were going to be skew, parallel, or intersecting. So actually, this exam has another one of these. Another good question. All right. So let's see. So we have L1 is going to be the line x is 2 plus t, y is 3 minus 2t, z is 1 minus 3t. All right, line 2, we have x is 3 plus s, y is -4 plus 3s, and then z is 2 minus 7s right here. All right, so what are we going to do here? Well, the question asks us to find the point of intersection. All right, but they also, if we look at the possibilities here, we see that there's a possibility where they have no intersection. So this is also a possibility as well. So they don't need to intersect anywhere. Now, if these points were, or these lines were to intersect somewhere, then their x, y, and z values will naturally be the same because it's the same point, so it needs to have the same coordinates right here. Oh, we have a question. Yeah, what are skew lines? Just to make sure we understand what that is. That means that they're not intersecting or they're parallel or parallel. So for example, we could have a line like this, and then maybe we could have a line that goes like directly under. And there could be like some height difference between these lines, and it kind of scoots underneath, for example. All right, so let's start setting these equal to each other here. So we have 2 plus t is 3 plus s. So what I'm going to do is I'm going to solve for t here. And t is going to be 1 plus s. Okay, so I used my x equation, and I found that if the points are going to be equal, then t has to be 1 plus s. Now what I'm going to do is I'm going to take that and I'm going to put it into the y equations. So anytime I see a t, I'm going to replace it with a 1 plus s. All right, so I see a t here. That's now going to be written as 1 plus s right here. Okay, because we found out that had to be true for the x equations to work. All right, now I'm going to distribute the -2. And then we have a nice little algebra equation for s's here. So 3 minus 2 is 1. And I'm going to add 4 over here to make 5. And then I'm going to add 2s over here to make 5s. So it turns out that the place where these guys are intersecting needs to happen at s equals 1. And then consequently, that means that t is going to have to be 2, because t is going to be 1 plus whatever s is. Okay, so now the final thing we need to do is we need to check to make sure that if we plug in this t value and this s value, we really do get the same point. Because we technically could have had these two agree right here, but then when we plug in the s and t value, it doesn't agree for z, for example. So that's what I mean like by a vertical shift here. So let's go ahead and check it out. So we have t is 2 here. That means we're going to have x is 4. We have 3 minus 2 times 2. That's going to give us -1. And then we have 1 minus 3 times 2. That's going to give us -5. Now, hopefully, fingers crossed, we will end up getting 4, -1, -5 down here. Let's see. So I plug in s as 1, I get 4. Okay, good. I plug in S is 1 here, and I get -1. All right, it's the drum roll time. It's time to see if this works out. We have S equals 1 in here. 2 minus 7 is -5. All right, wonderful. So they agree on all the X, Y, and Z values, meaning that 4, -1, -5 is going to be our answer. And thankfully, that shows up as one of our answer choices here. What would happen if it didn't work out? So like, let's say I got like a 4 here and a -5 there, then they would be skew, because in order for the X and Y to agree, we need these S and T values, but these very S and T values would make the Z's not agree. So there's no way that all 3 coordinates could agree at the same time. Now, one thing I failed to mention in this problem is parallel. So the problem doesn't give parallel as an option, so you can eliminate it for free on this. But how would I know if these lines are parallel? And the answer is we look at their direction vectors. So the first direction vector here, if we wanted to know if they're parallel, would be 1, -2, -3. And then V2 would be 1, 3, -7. Oops, got kind of eaten up here. All right, so let's see here. So they have the same coordinate in the first, in the X value here. So if they're going to be parallel vectors, that means they need to literally be the same vector, because this is a ×1 multiplication here. But -2 times 1 does not give you 3. So these are not parallel. If one direction vector is a multiple of the other, then we will have parallel lines here. All right, so that's those are some problems with intersections of lines and finding the line of intersection. I'm going to give chat one more chance to ask a question, then I'm going to ask a question for someone in the live audience. So why don't you guys go ahead and put in here what you guys want to do.
Dr. Manley,
Yeah, what's up?
if the 2 lines were perpendicular, would we have to get the points from the solving for T and S and then do a dot product to tell?
Well, you can tell if they're perpendicular even without solving for the T and S by just dotting their direction vectors. So you don't even need to do any of this to see if they're perpendicular.
Okay, thank you.
All right, let's see.
Wait, lines can be perpendicular without intersecting, correct?
Yeah, that's right. Yeah, you're just checking to see if their direction vector is 0 or not. Or sorry, the dot products of their direction vectors is 0. So yeah, that would technically count. Okay. Anyways, let's see here. I see some questions about cusps, curve on a surface. Quadric
Professor,
surfaces. Yeah, what's up?
I'm sorry to disturb you again, but did you say that perpendicular lines can may not it's possible that there are perpendicular lines which do not intersect?
Well, yeah, if you're working in 3 space, then perpendicular more refers to their direction. And if they're going at a 90-degree angle to one another, then that's their direction. So they're going to have a dot product of 0.
Oh, yes, that's true. In a 3-dimensional space. Yep. Thank you, Professor.
Yeah. Okay. It looks like we're going to have some questions on curves occupying a surface. So which surface does this curve end up being on? That seems like a common question here. Let's see. I don't remember if any of these were on the practice exams or not. Let me take a quick look here. Does anyone have a question about that? Yeah, what problem does that happen on? Okay, so here's a question from quiz 2 regarding this. So here we have a vector valued equation, and we want to see which surface this vector valued function will end up lying on right here. All right, so let's see here. Now, normally we actually even have the benefit of multiple choice. So technically we could take X, Y, and Z and check our way to victory. We could just plug X, Y, and Z into the equations that they give us and then see which one ends up actually giving us the same thing on both sides. Oh, they gave the names of the surfaces. Oh, okay, never mind. We can't do that then. I think I've seen a practice exam though where we did have that option. So if they list the equations, then we could just guess and check. I wouldn't recommend doing it that way because that takes longer than it needs to. What I would do is I see a sine and cosine pair here, right? So I know that whenever I see a sine and a cosine in a parametric equation, kind of like this, that kind of says to me that there's something circular going on here. So what I'm going to do is I'm going to try to square both of these and add them together and see what happens. So I have x squared plus y squared, which is going to be 4t squared sine squared plus 4t squared cosine squared. Okay, so here's the xy version, here's the t version. So what does this end up simplifying to? What is this going to be? 4t squared is right. All right, now we actually have a way of expressing t squared, that's z. So this is going to end up being 4z. So the surface that we're looking at is x squared plus y squared is 4z. That's the surface that this is going to lie on. Now we got a little bit lucky this time because it exactly worked out that it was Pythagorean. Sometimes we'll square these and then we'll maybe be off by a constant. In that case, I would multiply either x squared or y squared by an appropriate number, and then you'll have your Pythagorean identity going on here. All right, so the moral of the story here is that we just need to look for the Pythagorean or the circle pieces right here, and then we square them and try to get them to turn into something simpler right here. But now we need to identify the surface. Is there a question?
Some of us are confused where you pulled the 4z from.
Well, t squared is another name for z, so I just put z in right there. All right, so let's see. We need to see what kind of surface x squared plus y squared equals 4z is. All right, so let's see. So what we could do is we can look at the traces. If I maybe plug in x equals 0, I have y squared is 4z. That's going to be a parabola because I have one variable not squared and one variable squared. I do the same thing for y. I have x squared is 4z. That's going to be another parabola. And then finally, if I make z be some kind of constant over here, we're going to end up having a circle because we're going to have x squared plus y squared is 4 times some constant here. And so what shape is this going to end up being? So if we have a parabola, and a circle, or more generally an ellipse as our shape, well, let's look at the words that we have. We have a parabola and we have an ellipse. So this says to me that it's going to be an elliptic paraboloid. That's what this shape is going to be. And notice that this shape only works for k greater than 0, because you can only have sums of squares adding up to something positive. So that's only going to be positive right there. All right, so seeing what surface a curve is on, you essentially just need to look at the types of functions and figure out a relationship between them. And often when you have sines or cosines, that relationship is going to be the Pythagorean identity. All right, so we got this question here. Now let me open it up to the people live here. Does anyone have a question that you guys would like to ask? Anyone here? Yeah, what's up? Oh, like the quadric surfaces? Yeah, sure. Let's take a look at a quadric surface one. I think that was a high demand in the chat as well. So let's see here. We have a good one for that. Here's a good one. Let's see here. When we plug in z for the 0 for the trace, isn't it just a point? Yeah, that's right. And then if you plug in z as some positive number, you're going to get an increasingly large circle. That's exactly right. Okay, so I want to take a look at this question here. Consider this surface, 4x squared minus y squared plus z squared is 0. Which of the following are correct? The surface is a hyperboloid of one sheet. What do you guys think about that? Is this going to be true or false for this? Let's see. Yeah, both the in-class audience and the people online know it's false. Okay, so why is this false? Well, if we made actually one tiny little adjustment here, this would be true. If I replace this with a 1, then this would be true because we would have one negative sign next to our squares, and that will form a hyperboloid of one sheet. But because we have 0 over here and it's not 1, that's not going to happen. And yeah, I was going to ask what shape actually is this, and it seems like people are already answering that. This is going to be a cone because we can move the y squared over here and have 4x squared plus z squared is y squared. And when we have 2 squares on one side and 1 square on the other side, this is going to be a cone. All righty. So the horizontal trace in the xy plane is a hyperbola. What do you guys think about that one? Is that true or is that false? People are a little more hesitant on this one. False, true, true, false. Okay. We have some dissent on this one. Let's figure it out. So, by the way, I think I saw it before class started. Someone was asking about horizontal or vertical traces. The reason why this is called a horizontal trace is if we look at our normal 3-dimensional space right here, and we draw a plane, the XY plane, if this were a room, this would be horizontal or flat on the ground. There's nothing really special about that. They could have just said trace, and that would have been totally fine. All right, so the horizontal trace in the XY plane is a hyperbola. Well, if we're in the XY plane specifically, then we know that z equals 0, right? They're not saying parallel to the XY plane, they're saying in the XY plane. So z is going to be 0 here. So if we put that into our equation, we have 4x squared equals y squared. And this is not the equation of a hyperbola. In fact, if I took a square root, I'd have plus or minus 2x is going to be y right here. So this wouldn't be a hyperbola. These would be kind of like this X shape with these crossed lines right here, right here. You can maybe imagine it as like a degenerate hyperbola, but it's not really a hyperbola. All right, so that's false. Okay, what about the next one? The traces in the plane parallel to the XZ plane are ellipses. So this time we have the advantage that we could be parallel and not just in the XZ plane. What do you guys think? Oh, well, actually, we could use our testing knowledge because we know that P and Q are false. Then there's only one option available now, and it's going to be R only. So that's definitely going to be true based on just the exam. But let's understand why this is going to be true. All right. So if we're parallel to the XZ plane, then the equation of our plane will be y equals some constant right here. All right. So let's go ahead and substitute that into this. So we have 4x squared plus z squared is some constant squared. And if we divide both sides by k squared, we have 4x squared over k squared plus z squared over k squared is 1. And if we remember back from, I think, lesson maybe 5 or 6, this is the equation of an ellipse. So do we have an ellipse? Yes, we sure do. So that's going to be true right there. All right. So the shapes, unfortunately, I don't like to advertise memorizing too often, but that is one thing I might actually just stare at for a little bit, is that lesson 5, is it 5 or 6? I think it's 5. Whatever lesson with the quadric surfaces, and I would look at those, oh, it's a 6? It's 6? Okay, sorry about that. Well, I would go and look at lesson 6 and look at the different forms for each of the quadric surfaces right there. That would be something that I would just kind of memorize for this. And then with the traces, you can kind of figure that out on the fly by substituting in the appropriate number, which is usually 0 or maybe some general constant right there. All right, wonderful. So we did this problem for the audience, the live audience. Let's go back to the chat right here. How are we doing on time? Doing good on time? Oh, yeah. All right, so let me see, chat. What do you guys want to do? Let's see. I'll make sure to mute yourself if you're not muted. I see 14 and 16. I think 16 is from the practice exam. For the people saying 14, is that also from the practice exam? Is that what you're talking about? Or are you talking about, oh, 14 on this page right here? Ah, okay. All right, let's see. So it seems like there's a split between doing 16 on the practice exam and then 14 right here. So I'm going to do 14 right here. I'm going to do this problem, and then I'm going to do 16 on the practice exam because that seemed like a problem that a lot of people wanted to see. All right. Let's see here. So if the curve C is parametrized by cosine cubed in the I direction, sine cubed in the J direction, and 1, technically this is a 1, in the K direction, find its arc length for 0 to pi over 2. All right, so in order to use the arc length formula, what we do is we take the derivative. So let's see here. The derivative of this, if we use the chain rule, will be 3 cosine squared of t, and then we multiply by negative sine. Then the derivative of this will be 3 sine squared, and then we have cosine of t. And the derivative of 1 will be 0 right here. All right. So let's see here. Now that we have our r prime, remember that our arc length integral is the integral from 0 to pi over 2, or whatever our bounds are right here. And then we have the square root of each component squared and added together. So let's see, if I square this, I'm going to have 9 cosine to the 4th sine squared plus 9 sine to the 4th cosine squared. Okay, so now I need to do this integral in order to figure out what my arc length is. And initially, this looks really terrible. This looks like a completely awful integral to do here. But it turns out that there's some ways we can simplify this. So what's the common denominator of these terms? What goes into both of these? Yeah, that's right. We're going to have 9 sine squared cosine squared because at a minimum, the power of sine is 2 here. At a minimum, the power of cosine is 2 here. And then we have a 9 for both. So I'm going to factor that. 9 cosine squared sine squared. And then what's left over? Well, let's see. We have a cosine squared left over here. And then we have a sine squared left over here. I think we all know what this means. This is a very fancy way of writing 1. So we were able to simplify this by factoring here. So this is 1. This is going to go away because it's multiplied. And then I'm going to do the square root of 9 cosine squared sine squared. So I have the square root of 9 is going to be 3. Square root of cosine squared will be cosine. And the square root of sine squared will be sine. And technically, we would need to put absolute values on these. But in the interval 0 to pi over 2, both of these are positive. So we don't need to worry about that. All right, and then we just need to do this integral right here. Does anyone know how to do this integral? How do we do this one? Yeah, it looks like u sub might be a good option here. Let's do that. U is going to be sine of t, and du will be cosine. Although we could have done it the other way too. That would have also worked. All right, so we have 0 to pi over 2 is t, and then we have 3u du. All right, so this will be 3/2 u squared from t is 0 to t is pi over 2, and then we can switch back here. All right, and then let's go ahead and plug in pi over 2 in for this, and we get 1. And then times 3/2 will be 3/2 right here. And then we can plug 0 into here and we get 0. But regardless, we get 3/2. So that's going to be our answer for this guy. I think someone in the chat says you could use double angle for this. And that's absolutely true. So this right here, we can modify using the double angle formula. This is going to be 3/2 sine of 2t. So we also could have integrated it that way as well, if we wanted to. All right. Let's see here. So we did that one, and then I promised I would do number 16 from the practice exam, although I don't have that open right now. If someone could let me know what that is, I'd be happy to answer it. You got it? Okay. Okay. All right, thank you very much. All right, so for those of you who aren't in the audience, this is number 16 on the practice exam. And what this question is letting you know that u hat and v hat are unit vectors, meaning they have a magnitude of 1 right here. And they're also saying that the angle between these two vectors is 2 pi over 3. So we're going to call that theta. Now, what they want us to do is they want us to find u hat dot 2v hat plus 5u hat. And they never gave us specifically which vectors these are. So we have to use some other information in order to do this right here. All right. So I'm going to dot this right here. And remember, the dot product's distributive. So we could dot this and then add and then dot this. So we have 2u hat dot v hat, and we can move the constant out. And then we have 5u hat dot u hat. Okay. So we get here. Now let's worry about this one in a second. I'm going to keep this the same for now. But what is this going to be right here? What is this number? Looks like we have some conflict between 0 and 5. So this is actually going to end up being 5. So for unit, or actually for any vectors, if you dot a vector with itself, it's going to be equal to the magnitude of that vector squared. Now, what are the magnitude of these vectors? They're 1. So we end up getting that this is a very fancy way of writing 1, and then 1 times 5 will be 5 right here. All right, so this is 5, but now we need to know how to evaluate u dot v. Well, this relies on us knowing about the other formula for dot products. So where u hat dot v hat is the magnitude of u hat times the magnitude of v hat times cosine of the angle between them, which is 2 pi over 3. Now, what are the magnitudes of these? Well, once again, they're unit vectors, right? So this is just going to be 1. And then we have cosine of 2 pi over 3 right here. And then what's cosine of 2 pi over 3? Yeah, it's going to be negative 1/2. Absolutely right. So we end up with negative 1/2, but then that's times a 2 right here. So this is negative 1 plus 5. It ends up giving us 4 right here. All right, so this is an excellent question, seeing how much you understand dot products, because you needed to understand that they were distributive, that you can move constants out, that when you dot a vector with itself, you get its magnitude squared, and it tests to see if you know the other formula for the dot products. This is an excellent question on dot products right here. All right, so we did those. Let's get another question from the chat here. I think we have time for at least one more. Do you guys have any other questions? (19, 11). Remember, no cheating, no saying it more than once. Oh, I saw a question I can answer right now. When will this recording be available? I'm going to post this right after I'm done teaching my next class. It'd be kind of pointless for this to wait till tomorrow at noon. All right, it looks like 19 on the practice exam is winning out here. Sorry for those number 11. You guys were a close second, I think. All right, can someone regale me with number 9 or 19 from the practice exam? What was that one? Oh, this is an equal sign. There we go. Oh, it's a find the curvature one. Yeah, LaTeX does not copy well. Okay, so find the curvature of, and then let's see. Yeah, read it for me. It's kind of hard to read that.
It's t squared plus t.
Oh, I already got someone to read it, but thank you.
Oh, you did? Okay, okay.
Okay. All right, so let's go ahead and do the curvature here. Now, when they just give you what R is, and they don't ask you to, find like the unit tangent vector or anything in addition to this, I would go ahead and just use the R prime cross R double prime formula. So kappa of t is going to be the magnitude of R prime of t crossed with R double prime of t divided by the magnitude of R prime of t cubed. Okay, so let's see. So we need to do some derivatives here. So let's go ahead and do that. So the derivative of this will be 2t plus 1. The derivative of t will be 1. And then the derivative of ln of cosine, so we have 1 over cosine, and then we multiply by the derivative of cosine. That gives us negative sign. But there's a more compact way of writing this. This is negative tangent of t right here. All right. And then we're going to do another derivative because we need that. The derivative of this will be 2. Derivative of this will be 0. And the derivative of negative tangent of t will be negative secant squared of t. Okay, now we're not just interested in finding kappa at any t value. We want to know what it is specifically at 0, 0, 0. By the way, what t value does that correspond to here? T is 0. Yeah, that's not really a big surprise here. Yeah, it's the only thing that can make that be 0 for sure. So we're really just looking for kappa of 0. All right, so that means I'm just going to use R prime of 0, which is 1, 1, and 0, and R double prime of 0, which is 2, 0, negative 1. So I would definitely use these vectors as opposed to taking the cross product of these functions. This one isn't too bad to do in the function form. There are some problems like this that are awful to do if you don't plug in the specific number. So be sure to plug in the specific number before you do this. All right, let's do ourselves a cross product here. So R prime cross R double prime. Okay, we have I, J, and K. 1, 1, 0, 2, 0, negative 1. All right, and so for the I, let's see, we have negative 1 minus 0 is negative 1. All right, for J, we have negative 1 minus 0, but then it's going to be made into a positive 1. And then we have 1 times 0 minus 1 times 2 ends up being negative 2. All right, so we get this, and then the magnitude of this vector is going to be the square root of 1 squared plus 1 squared plus 2 squared, aka the square root of 6. All right, and then so we know we're going to have a root 6 in our numerator right here. And then what we're going to do now is we need to figure out the magnitude of R prime. Well, let's see. The magnitude of R prime is the square root of 1 squared plus 1 squared. All right, and then this is just going to be root 2. All right, so then I have this, and then this is going to be cubed. So I have root 6 over 2 root 2. And this is going to be my answer right here. Although I think on the, I don't know if this was a multiple choice one or not. I think they simplified this a little bit. This ends up being the same thing as root 3 over 2. Because you effectively divide out a root 2 on the top right here. All right, so there we go. So there's a nice curvature problem. Unfortunately, the nature of finding curvature is that it's complicated. We have to, even for a relatively simple curvature problem like this, we have to do a bunch of different steps. So unfortunately, it's easy to make a little mistake as you go along. So when you're checking your work, be especially careful to check your curvature problem because there might be an arithmetic mistake. All right, looks like it's 2:45. So that's all the time we have for now. Let me go ahead and stop the recording here.